Hello everybody, welcome to this talk. I will discuss about a personal project I did, which is writing a Nintendo DS emulator in Go. I've been writing emulators for many years in my life, since I was very young. I also contributed to the MAME emulator, which is the main multi-arcade emulator, many different drivers in there. So it's one of my personal things that I find more interesting in programming. And so when I learn a new language or a new framework or a new technology, after like maybe the first couple of years that I get familiar with it, I try to write an emulator in it because it really stresses the performance side, optimization side, which is something which I'm really interested into. So a few years ago, after I got familiar with Go, I decided to look into a new system to emulate using this technology, and I picked up the Nintendo DS. The emulator is fully open source. It's available at that address. It's been from scratch, so you can follow the whole history if you want. The talk will basically discuss, there will be a brief introduction on how video games hardware works and how you usually go for emulating it. And then I will focus on how to emulate a CPU with Go, a memory map with Go, some 2D and 3D graphics emulation tidbits. That will be like a full workshop. Of course, how to do 3D emulation is a really complicated topic, but I will just give you some ideas. And in general, I will try to explain enough of the background necessary to get some insights on how Go helped my work or what problems I had to fight against in Go. So there will be a few lessons learned that I think that are useful in general in Go programming. So let's begin from the hardware perspective, because when you emulate a video game, you need to, of course, begin from the hardware. So if we take one of these, Pac-Man, this is Pac-Man from Midway, from the 80s, is one of my favorite platforms because it's very easy to emulate. I actually have a one-day workshop to write an emulator from scratch in C that I run over the years. It's a very, very nice, simple hardware. And it's a game from the 80s. So how does it work? How in the 80s you were able to do games like this? Well, the answer is not with a computer, but with lots of custom hardware. So you had these large PCB boards with lots of custom chip on it. So you had custom chip for everything. This is, of course, something which is expensive right now. So right nowadays, what, of course, the electronics industry does is to build the system on chip, which means everything you see there is just one chip. But back in the days, of course, you had a lot of custom chips everywhere. And for instance, this one is an actual Pac-Man PCB. If you just have one in your hand or you have a high-resolution picture, you can actually discern what each chip means. So for instance, you can immediately tell which one is the CPU, which is a Z80. It's an old 8-bit CPU. And which one are ROMs. ROMs are, of course, the memories, the read-only memories where they actually game code, graphics, and audio information are stored. There are a few of them. And then there are all dedicated chips. And everything needs to be emulated. So if you abstract a little bit from the physical board, you can see that there are basically chips, like running subsystems, so to speak, and memories. So these two different kind of things that you need to cover in your emulation. Subsystems, as I said, there can be many different of them with the very custom workings. So for instance, you can have one or two or more CPUs. You can have one, two or more GPUs. You can have floating point accelerators. You can have audio, mixing, hardware effects, specific crypto stuff. There was a lot of crypto stuff, especially in early games for copy protection reasons, of course. And you can have like DMA, which is something that we take for granted within a chip right now. But back in the days, for instance, the DMA was an external chip that was used by the GPU to transfer memory fast. And then you have different kind of memories. If you compare to like a standard PC architecture, where basically each CPU has access to the same hardware, so you can do everything from each core, and the kernel makes sure that you basically balance your workload across the core because they are the same. Basically, they are duplicates of the same CPU. In video games hardware, it's very common to have different CPUs that access different subsets of the hardware. So maybe one CPU can access only a few things, another CPU can do other things, and so you have one program for CPU 1 and one program for CPU 2. And you have different kind of RAMs, like RAM dedicated for video, dedicated for sound, and so on. So this is a map to show that, like, for instance, a two CPU system, they have two different buses through which they access different hardware. So maybe they can have different working RAM, not in common. They have different RAMs, so there is no shared memory between them, for instance. They can only communicate through, I don't know, a serial channel, so sending 1 byte, and on the other side reading 1 byte, and there is no RAM in common, for instance. This is, of course, completely different from the PC architecture, but it's really common in video games hardware. So Nintendo DS, for instance, has two CPU. They are two ARM-based CPUs, one ARM9 and one ARM7. They are respectively 66 megahertz and 33 megahertz. They have a total of 4 megabytes of RAM, so not that much by today's standards. And of course, the cute handheld console had two screens, right? So the Nintendo designers put two different GPUs, identical, one per screen, for 2D graphics, and then just one GPU for 3D graphics. So basically, Nintendo DS, you could run 3D graphics only on one screen at a time. So you either have like your main game on the top screen and maybe like the map in the bottom screen, or if you wanted to have 3D graphics on both screens, the trick was to draw one frame of 3D graphics on the top screen and then the frame after on the bottom screen. And so switch every frame 60 times per second, and so you have like a two 30 times per second 3D screens. And this was very common in games. Then you have some sound support for 16 digital channels with a lot of effects and lots of custom hardware. So hardware timers, hardware divisor, because the early ARM chips didn't have a division opcode. So if you needed to divide the two numbers, it was very slow. So the Nintendo designers put a chip specifically to two divisions that the CPU could use. Actually, it was division and square roots. And Wi-Fi support, encryption chip for copy protection, and so on. So how do you usually structure an emulator for this kind of hardware? So we said that there are many different subsystems, many different chips on the board, and they are all running in parallel, right? They are different chips with their power, and they run. So basically, you can think of all of them as a different like process in your code, a different subsystem, executing at a different speed. So for instance, the first CPU is double the speed of the second CPU. And then you have the audio chip, which is producing 44 kilosample per second. You have the DMA, which is copying memory at 200 megabits per second, if it was told so by one of the CPUs, and so on. And they all run in parallel. So historically, what emulators writers did was to basically serialize everything, interleaving emulation, like this. So, for instance, let's say that you interleave every frame, your emulation. So in the first frame, you want to emulate one frame of graphics, which is 1/60th of second, because you run 60 frames per second. And so you need to emulate the first CPU for 1/6 of a second. So if the speed of the CPU is 66 megahertz, which is around 66 million instructions per second, 1/6 of that is about 1 million opcode per second. So you emulate 1 million opcode of CPU 1, 500,000 opcodes of CPU 2, because we said that is half the speed of the first one, and then draw one frame with one GPU, and then draw one frame with the second GPU, and then produce 700 samples of audio, which is again 1/60th of a second, and then your frame is finished. And then you move on to the next frame. So you basically, instead of emulating everything in parallel, you basically emulate them sequentially, interleaving, with a fixed amount of time that you allocate for each subsystem. So this is very simple emulation approach that unfortunately doesn't work very often for many hardware, because video game programmers try to use the hardware to do all kind of funny effects and funny stuff. So for instance, this one, let me see if you can see it. The contrast is low. There is kind of a wobbling effect, if you can see it. You see? It's like wobbling. So to do this effect, the video game programmer didn't, actually the GPU couldn't draw a wobbling stuff like this because it was just copying sprites and pix maps. So the effect is done by a clever programmer that basically changes the horizontal scrolling of the GPU every line of screen with the CPU. So it waits one line, and before the second line goes on, moves the horizontal scrolling register a little bit, every line of screen, synchronizing with the GPU while it's drawing, okay, to do this effect. And so it doesn't need a GPU that is able to actually do that effect. It can just simulate it like this. So if the CPU, changes a GPU register, sends a command to the GPU every line, and needs to affect the drawing every line, you cannot interleave frame by frame because it's too much. You would lose effects like this. So what we actually do in emulation, instead of interleaving every frame, we interleave every line of screen. So we were interleaving 60 times per second. We are now interleaving much more, about 11,000 times per second, which is basically the result of 60 per 192, which is the height of the screen. So it's about 11 times per second. And so you emulate the CPU much less than before, each CPU. You produce only 3.8 samples of audio every time, and then loop like this. And every time you just draw one line and produce just 3 samples of audio, and so on. And you need to do this fast enough to be able for the games to be playable, so real speed, 60 times per second. So this is actually what we do normally in emulation, and this was part of my background when I approached writing the Nintendo DS emulator in Go. And so the first thing that came to my mind was, okay, we have this Go with this wonderful Go routine, concurrent programming. Why don't we do everything in parallel, like this? So why don't we emulate subsystem in parallel? CPUs, for complex reasons, need to be emulated serially. I won't explain why, but there are syncing problems. But after CPUs are run, all the other subsystems could potentially be run in parallel. So, and this is what my emulator does. My emulator emulates one line of CPU 1, one line of CPU 2, and then runs every subsystem emulation in parallel. So the 2 GPU for bidimensional graphics, the GPU for 3D, the audio, the DMA, all runs in parallel through different Go routines. Which is actually nice because, of course, it uses all the cores of my laptop. But it's actually not that fast because basically all these Go routines are syncing about 11,000 times per second, which is actually a lot. This is something that I discovered while writing this. Before, I didn't have a clear idea of the limits of the runtime of Go. So actually, the first approach was to spawn a new Go routine for each subsystem, for each line of screen, which is spawning 6 or 7 Go routine 11,000 times per second. That was absolutely too much. The computer wasn't able to cope with it. So spawning about 80,000 Go routine per second, it's a no-go. Keeping the Go routine running, so I have one Go routine doing audio emulation that just needs to sync every line. That is actually doable, it works. But still, if you profile my emulator, you will see there is a lot of mutex contention, there is a lot of performance issues with syncing. So it's actually working as a proof of concept, but it's probably not the correct approach. I think that it's too high, the frequency of syncing for Go. So we need probably to lower it somehow or just drop this architecture in the future. So how do we go with CPU emulation? This is an example of a CPU interpreter. It's just a pseudocode, but like if you have a CPU structure with a run function, and you tell it to run until a certain point in time. Okay? So it's looping until the clock reaches that point of time, and then it's basically doing a standard computer science CPU loop, which is fetching a single opcode from memory, from the current program counter. Then it's decoding this opcode to see what kind of opcode has been fetched, and then it's emulating it using a table of function method pointers. So that like I fetch an instruction from the memory, I see that it's, I don't know, a multiplication instruction, and then I execute it through this function pointer table that you can see. And then increment the clock and get emulating. This is just pseudocode, but the real code is quite similar. And this is an example of a theoretical add instruction to some two registers and put the result in a third register. You can see there is some bit twiddling to extract different information from the opcode, and then there is the actual sum going on between two source registers into the destination registers. And then it's moving the program counter forward by 4. In this case, the opcodes are 32 bits, so by 4. So this is just a theory of how emulation, interpreter emulation works in any language, including Go. The real world is a little bit more complicated, of course, and there is also some optimization going on for several reasons, but it's not that different. I don't have a pointer, actually, but you can see that binary little endian, that one is fetching from memory the instruction, incrementing the clock, and this op-arm table stuff here is basically calling the emulation function, and then it's looping. So it's not that different. Of course, this code is very, very hot in the emulator, so it needs to be very careful rewriting it. There is also a trace hook for debuggers, so that I can, interrupt emulation at any instruction in case I want to do step-by-step debugging. And then, of course, you need to write the actual opcodes. And ARM is a very complex processor because it's got 2 instruction sets, not one. It's got 2 instruction sets. And there is the ARM instruction set, the thumb instruction set. And each of it has many opcodes which are CISC-like. So that is, they have many, many variations, a small variation, like you can have an addition with flags, without flags, with a barrel shift, without a barrel shift. So it's a really complex instruction set. So I had to write many, many different variations of the same opcode. So at some point, I realized that I had to basically generate the code for that. So I wrote a code generator for the instruction sets, which generates about 30,000 lines of code, like this. This is one of the many different addition instructions. There is a lot going on, but at the end, you can see, like there, res equal to rn plus op2. That is the addition, the real addition going on. And then there is a lot of stuff going on. And of course, for this kind of stuff, we could use some kind of generics. Some kinds, actually not really generics the way the Go-Do Traf design is going, because those are really generics from the point of view of making like a data structure with a static type. Here we will need something like more macros, so something that let you generate code from templates, basically. You need some template of code and then generate it. Like in C++, we can do this with the C++ templates because they are very complex, very, very complex and powerful, so they can be used also to do macros. So sometimes I try to emulate the processor with the C++ templates and it works. It's very, very slow at compiling, of course. But with Go, we would need something more like some kind of macro support, which I don't think it's on the radar right now. So for now, code generation is the best approach. And it's actually easy to debug, because if I feel there is like a bug here on this specific opcode, I can just put a print there or something, and I'm debugging this instance of the function. If you have like a template in C++, if you get the print, if you put the print at a certain point, it gets duplicated on all the different instances, so it's more complicated. Here, it's very, very easy to debug. So code generation actually was not so bad experience for me. I also wrote a JIT for the ARM processor just to speed it up. It's not based on LLVM because it's a complex. If you ever tried to use LLVM as a library, it's actually a huge library, it's complicated. So I wanted to do something more easy, just to just to explore the Go runtime. So I wrote a manual JIT. I'm using this library, GoJIT, which is unmaintained, and it's just a basic minimum. It allows you to allocate a block of memory where you can write x86 opcode on it with some helpers and then jump on it to call a function. That's what GoJIT does. And so I use it to write a JIT. So it's a translator from the ARM opcodes to x86 running within the interpreter. It's about 2,000 lines of code, so it's not that much, as you can see. You can have a look if you want. This is an example, but it's basically at the end, you're just generating single opcode. So, for instance, the mov L, that is one of x86 opcode. It's a move instruction. So with that line, I'm generating one mov L instruction in the current buffer, blah, blah, blah. The JIT is working, is a little bit faster than the interpreter, not that much because it's not optimizing anything. It's really a bare bone JIT. So it works, but there is a big problem because it only works correctly with the garbage collector disabled, which means it cannot be really used for real. But because the problem is that, you know that the garbage collector is like walking the stack of all your function and Go routines to find the allocation. So it needs to have a precise information of stack maps. Stack maps are generated by the compiler in your code and tells the garbage collector, okay, in this function, this variable here is a pointer and it's saved on the stack. And the garbage collector needs to know to follow all the pointers. So basically, when I generate a function in memory with the JIT, I have no way to tell the runtime where the pointers are. There is no hook. There is no API in the runtime to provide stack maps. And so basically, as soon as I run the first function, the garbage collector triggers. It finds in the stack one of the generated JIT function and immediately panics the runtime and abort the program because they say, okay, I don't know this function, where this is coming from. I never heard of this function. I have no information. I cannot walk the stack. Bye-bye, and panics the function. So you need some kind of API support from the runtime in case the Go team wants to support writing JIT in Go in the future. I also wrote a test suite to stress the JIT with the interpreter and make sure that they match with lots of random inputs to make sure that they have no bug. And to debug, I wrote like a textual debugger interface, very easy, very bare bone, just to make sure that I don't go crazy with the prints and logs. Okay, for memory map emulation. So we said that there is a CPU with a bus accessing different chips and memory. How does it access, actually, those chips and those memory? What is the bus? Is it a PCI Express? No, it's not. It's not a serial bus. It's just memory. They are just memory mapped, so to speak. So what it means, memory mapped? It basically means that every bank of memory and every chip, every register chip is available in memory at a fixed address that can be accessed directly by the CPU writing in memory at that point. So for instance, this is the real memory map of Nintendo DS. We have one bank of RAM accessible in those address ranges, one bank of ROM, GPU register, 2D and 3D. So for instance, if I were to write in Go some code running on Nintendo DS to access a specific register in memory, I would do like this. There is like a register constant, with a fixed address coming from a memory map, and I would just write some data in there. Okay, so the chips are just mapped in memory, just need to access a fixed address. And by the way, does anybody know what this number is coming from? 53208? Nobody? Okay, so I'm the oldest in this room. That was actually the same concept on the C64, and it's a graphic register to change the border color, like the example was. If you write this command on the C64, poke, which means write to memory, poke, you put the address, 53208, and then 1 is the color white, and 2 is the color brown. And you see it's changing the border color. So it's the same concept. So you have a fixed address in memory where you just write some bytes and to communicate with the chip, with in this case, the graphics chip. Okay, so how do you emulate this? Well, the simplest approach is like this. I need to write a function, for instance, to read from memory at a certain address. I just do a switch. If the address is here, I access the RAM and I read the byte. If the address is here, I forward to the GPU emulation to read the register. So this is the simplest approach, which is not very scalable, right? Because, for instance, we need to write many of these functions, one for 8-bit, one for 16-bit, one for 32-bit accesses, for reading and writing, and repeating every time the same address switches. And it's also not very, let's say, how do you say, divided into modules. All the knowledge of the memory map is here. So what I try to do in my emulator is try to have like more of a declarative approach to the memory map. I want to do something like this. I want to have a single point where I declare all the addressing and binds memory banks and chips to specific ranges. So for instance, this is real code from the emulator. You can see the first lines are mapping memory slices to the bus. So you have the address ranges and the slices of memory mapped there. And then the second block is mapping chips, so I/O registers, memory mapped registers. And if you want to see how a single chip works, it's like this. So this is, for instance, is the hardware divisor I was discussing before. You can see that the first line is mapping the hardware divisor at a certain point in memory, certain fixed address. And then from there are several different registers which are defined through struct tags, using struct tags of Go. So for instance, let's say we get the res register. Do you see the res register? It's the result. Res register, if you read that line, it's a 64-bit register, reg64, that's the type of the variable. And then with the struct tags, I said that, I don't know, offset is 0x20, so it's 20 hexadecimal from the start of the bank above. So this is placing the register in memory, and when the emulator accesses that address, basically the execution go reading directly within this register in this structure. So it's a fully declarative approach, and then there are some features, options that I can add, like RCB means read callback, which means I ask to this library, please call a callback as soon as somebody try to read from this register, because maybe I need to do something. In this case, the callback is just a method on the hardware divisor class with a special name, and through reflection, it's called, basically. The method is called readRes. So it's the reflection calculates the method name and just call it. So this is just a declarative way of accessing the memory map. But of course, we also need to basically optimize this loop, as I said before, right? So to optimize this access, how do you optimize this once you have a fully declarative approach? You need a data structure to basically save all these range addresses and be able to quickly look up for given an address. And to do this, I use a radix tree, which is a data structure which is used to find usually words with common prefixes, using common prefixes to quickly find the differences in the word and isolate the word. I will explain with an example. It's much easier than it seems. So let's say I want to map in a radix tree those four objects. There are two memory banks, RAM, ROM, and GPU. It's the same example as before. So what I do is basically I just look, I want to look up. So I want to look up an address. So what I do is just I look the first byte of the address, which is highlighted in red here. I look the first byte. So since I was just mapping those four objects, if the first byte is 02, I am sure that I'm accessing the RAM, because all the other objects have different addresses, right? So if I just look in the first byte, I see 02, I access the RAM. So I can create a lookup like this. I start from the root, look at the first byte. If it's 02, I go to the RAM. If it's FF, it's the ROM. But 04, it's not enough to disambiguate, because there are two different chips that have the same 04. So I need to recourse to the second byte, which is again the same, 00, so it's not enough. I go to the third byte, and then I can understand which object I'm accessing. So this is the complex radix tree from this example. When there is a lookup in the tree to access a certain address, I just check 1 byte at a time, and with this lookup table arranged as trees, I find the correct chip. This is the data structure, very easy. So a node has exactly 256 children, 1 per byte, and then a tree is a pointer to the root. And this is the search function, which is it's just a loop, looping each byte, extracting the key there is extracting 1 byte at a time, looking up in the children array, and then if it's a node, it will recurse. If it's a leaf, it will return. Okay, some explanation of graphics emulation. So a GPU in graphics hardware is actually a chip that is able to copy block of graphics, which are called either tiles or sprites, depending on how you use them. So it's usual for video games to have graphics like this, where basically, for instance, the maps are made with blocks of graphics repeated and stitched together. And so usually the GPU was able to basically read those graphics from the ROM or from the RAM and just quickly copy these block of graphics together and put them on the screen with certain offsets or graphics effects like transparency and stuff like this. So the GPU emulation is about 2,000 lines of code. You can find in the source code within the directory 2D. It's very easy. And it's rasterizing pixel by pixel. It's not very, I would say it's not very interesting piece of code because it's just implementing all kind of 2D effects that Nintendo DS can do. There are many of them. But one thing that I think it's interesting for Go programmers is that from day one, I tried to understand whether bound checking was going to be a problem for 2D emulation because I need to copy graphics. So you can think you can have like a source graphics, which is like a slice of memory, destination graphics, which is another slice of memory, and I want to copy pixels from one to the other, making many accesses to copy those pixels. And so you have bound checking accesses on both sides. So from day one, I knew that bound checking was probably going to be a problem. So basically, I abstract with 2 different implementations of accessing a line of pixels. One, it's 100% safe code. It's using a slice with an offset. And the other one is unsafe code. So I have a uint pointer, which is an unsafe pointer to memory. And so basically, my code is able, with the build tag, to switch between a safe and unsafe version so that I can measure the results. And of course, the results are very easy, which is that basically the safe version is not able to, you're not able to play games or something like that. A bit better, and now, no, it's not that bad. It's not that bad, but it's still measurable. So by default, I build with the unsafe version. While developing, of course, I use the safe version to catch mistakes in my code. And so to try to solve this problem, I actually worked with the Go team, and I sent a few patches to the Go compiler to improve the bound checker, the bound checker elimination pass, which is called prove in the Go compiler. Prove as in you can prove that the bound check is not needed, and if you can prove it, you can not generate it, you can remove it from the code. So I sent a patch series that was merged for Go 1.11, and actually there is a paragraph in the release notes. And now the Go compiler is able to do more aggressive bound checking elimination. For instance, it can understand the transitive relations between variables and stuff like simple arithmetic accesses and stuff like that. This is a work that I contributed back in the previous cycle, so it's now in Go, available in Go 1.11, and it gives me about 8% of raw performance. So this is not a micro benchmark. Huh? It's not a micro benchmark. Would be, I don't know, 80%, 90%. This is a total time of running emulation with everything inside. Just removing bound checking from the graphics emulation, it's about, the improvement, sorry, I did is about 8%. So it's not that bad on the real world code. And this is something I want to show to people. Sometimes in the Go issue tracker, I see there are people that try to explain that the bound checker is not that bad. Nowadays, CPUs are fast and the branch predictor, and at the end of the day, it's not a big problem. No, it is a big problem. It depends maybe on the code, right? Not on every code, like everything. Not on every code, but sometimes it can be a really big problem. 3D GPU. Again, I did the software rasterizer by hand, no OpenGL, so drawing pixel by pixel, applying effects. Again, I'm using code generation, but I'm skipping because I'm late. One thing I wanted to say is that I'm using fixed point because that's the way Nintendo DS was working. And you can see here, for instance, an example of fixed point library I wrote. Basically, you need comments to understand what's going on, because without operator overloading, you are not able to write scientific code. So, like, if you see the comment, is a formula. If you know some 3D math, is actually a simple formula. But if you see the code below, you don't understand what's going on. This is because there is no operator overloading, so you cannot write like vector math in Go in a way that looks like math and not function calls. Fixed point library is all copy and paste code again because no macro support. And so quickly conclusions, performance, bound checking can kill performance, so it's not 2% or something like sometimes I read on the Go issue tracker. You can spawn 11,000 algorithms per second. You can sync 11,000 per second, but it will show up in the profiles. So depends on what you need, it might work or might not work. Missing from Go, more performance from the compiler for sure. LLVM is still better for sure. Operator overloading, macros I discussed already. And also some SSE intrinsic support will be great because in emulators, graphics programming in general, you want to, I don't know, maybe you could compute 4 pixels at a time with intrinsics. With SSE, you cannot do that in Go. Also for cryptocode, Go uses assembly to use intrinsics, but that's a problem. A good approach on Rust is to use vector types. So this, I think, is a good avenue that Go could use to expose vector types and then let the compiler generates SSE opcodes from vector types. And the stack map for JIT. Okay, just last thing, I will show you the emulator running once, just because it's more true. So you can see these are 3 games running in parallel, 3 instances of the emulator. The first one is Zelda Phantom Hourglass, then there is Mario Kart DS, and then a Metal Slug, very popular games, I hope you know them. And you can see the emulator is emulating the 2 screens, like a real DS, one screen on the top and the other at the bottom. And for instance, the Mario Kart in the center, you can see 3D graphics top and bottom. So as I explained, it's 30 FPS actually, because it's switching every frame between the 2 screens. And while in Zelda, for instance, there is the 3D graphics only at the bottom, and the top is just a 2D map. So this is emulation working, and there is also audio that you cannot hear now, but it's working that as well. You can compile it off GitHub, it works. Just pass a game to it, and it will work. Thank you.